We also like to hear from graduate students who are bringing in new ideas and who are our next generation of scientists that we'll be listening to at the 20th or the 30th Restoring the West Conference. So the first of those is Colton Finch. Colton is a PhD student in the Watershed Sciences program here at Utah State. It's kind of interesting. So he was at the University of Florida studying how dams affect fishes, and now he's moved back to the West where he's from, and he's looking at how fire affects aquatic species. Colton.
Thank you. I'm flattered to be able to be here and to talk after so many professionals, and I'm really lucky actually to get to be a part of the Fish Ecology Lab at Utah State with some support from the Ecology Center. And I'm a Quinney Fellow, which is a generous fellowship that allows me to do some of this work. And work a lot with, primarily with the Division of Wildlife Resources, but also with a lot of in-kind support from the Forest Service. So it's a really neat opportunity for me. Today I'm going to go through it'll be a little bit of a change of pace, right? I only have about 12 minutes, so hopefully I can keep on task. I'm going to be following an outline similar to a scientific paper, give a little bit of introduction and background, then talk about what methods I used to address my question and show you the results, and then a little bit of implications at the end. I'm really grateful that I wasn't the first speaker, for Jen and Peter and people that have gone before me, so I don't have to belabor this point a great deal. This is a study by Veblen and others on the Colorado Front Range that was examining the frequency of forest fire in the historic past, as well as in prehistory. So on the x-axis you have the year going all the way back to 1600. This is a cumulative distribution function of how many trees they had, which we won't worry about right now. But what this plot demonstrates to us is that before about 1900, fires occurred a lot more regularly in this area. It's mostly ponderosa dominated. That these fires were pretty variable in size. So some of them scarred up to 60% of the trees in that area, and some of them scarred less. But what we've noticed since 1900 is that the frequency and the scale of these fires has been greatly reduced. The reason that this is important is because you have a lot of native species, such as Bonneville Cutthroat Trout, that evolved with this historic fire regime, going off this way millennia. That's the environment to which they are adapted, as opposed to the environment that they're currently encountering. So these fish have specific life history characteristics and ecology that allows them to persist in the face of these kinds of disturbances. And what we're trying to figure out is how can we project this into the future to ensure the conservation of species of concern, like Bonneville Cutthroat Trout. This is a little model that I built demonstrating the likely impacts of fire on fish habitat. And the point of this is to demonstrate that fire isn't bad, right? We've already heard about this today, that fire isn't universally detrimental to fish. On the x-axis here is time in years. I projected this out 50 years. On the y-axis is some measure of habitat quality. And you could think of this gray line as like mean habitat quality over this interval, right? And if you have short interval fires, right after the fire occurs, you would have some decrease in habitat quality for a fish like Bonneville Cutthroat Trout, after which the ecosystem recovers and you may actually see an increase in habitat quality because of the incidence of fire. And this repeats, at this short interval. If you have a really long interval fire, you would likely see a similar response, except that the duration of the response is much wider, right? You would have a longer period of detrimentally affected habitat followed by a longer period of improved habitat. So on average, fires don't do any harm or any good, but at any one point in time here, you could, the conditions that you're observing would be reflective of the fire history. So short term, we know that fire has important habitat effects on cutthroat trout. For instance, post-fire erosion often reduces channel complexity, and we know that channel complexity is important. These fish are all looking for bioenergetically positive feeding locations. And so if you're living in a stream like this, just perched on a gravel bed, it's like living on a treadmill. And so that makes it harder for these fish to make a living. You also lose a lot of riparian vegetation for some time period after the fire, which increases water temperature and can change the food web. So all of these have important short-term impacts on trout. Of course, the long-term impacts, we know that as all this sediment that's introduced in the channel gets redistributed, you can have areas of spawning gravel that are really important, the development of backwaters and low-velocity areas for rearing, the introduction of large woody debris. As all of these trees recruit into the channel, that introduces habitat complexity that's really important. And then you maintain some of the vegetative complexity. In my study site, a lot of these upper elevation locations were dominated by conifer forests, almost complete canopy cover. There's not a lot of sunlight that makes it into the water. And so you can reset some of these streams back to a more open characteristics with fire. So the population effects on Bonneville cutthroat trout, this is an ash flow that killed a significant proportion of the fish in my study site after a forest fire. So in the short term, we know that there are losses. But in the long term, we suspect that the incidence of fire is neutral or gain on Bonneville cutthroat trout populations. But that's given that they've only been locally extirpated from a portion of the watershed, and that there's connectivity for those fish to return, as well as they don't have to fight exotic species. So Patrick yesterday introduced the Twitchell Canyon fire. This was a fire that burned in 2010 in south central Utah in the Fish Lake National Forest. It burned about 45,000 acres, and what was unusual about the Twitchell fire specifically is that about 2/3 of that affected area was moderately or severely impacted. And so we suspect that might lie outside of historical trends. What also makes this a really interesting study site is it's far enough south that it's regularly influenced by the North American monsoon. And so the reaction of the watersheds to fire are different than what you would see even in northern Utah or up into the Pacific Northwest. For instance, the 4 highest flow events that have ever occurred have all come because of monsoon activity, not because of spring snowmelt. And 3 of those 4 events, we've got almost 60 years of streamflow record in my study site, and 3 of those events have all come since the 2010 Twitchell fire. So there are a lot of changes happening. This is a map of the area, so you see where we are down here in south central Utah. This is the Clear Creek watershed. It's part of the Sevier River, which is its own endorheic basin. And there are 2 tributaries that I'm going to be talking about today. Shingle Creek over here and Fish Creek over here. These are 2 tributaries that would have formerly been connected, but are now disconnected because of a series of fish barriers that were built to keep exotic fish from repatriating this watershed now that all the other fish are gone. And this is the footprint of the fire. So what we know from Patrick's analysis of the Twitchell fire is that this fire is the 1%, right? This is the large fire that occurred and affected a significant proportion of the landscape. And this place is especially important because for the Southern Geographic Management Unit of Bonneville Cutthroat Trout, it's a high priority watershed. This is actually the largest watershed in Utah that has no exotic species in it. So it holds a lot of promise not only for cutthroat trout but for other species. And it's part of a range-wide conservation agreement to keep these fish from being listed. So this is an important metapopulation. A metapopulation is a group of populations where fish flow across the landscape from one location to another. And what we know about this is in the future, it is going to be perturbed again by fire. And so what I'm interested in looking at is what management options do we have in this scenario to increase the resilience of this important population. I'm using models to inform this. I've used them to capture what we saw as a result of the Twitchell fire and to model it into the future. And the 2 things that I was most interested in is synchrony of fire. What we observed is that most of these 2 watersheds burned at the same time. I'm also interested in connectivity. This is one of the fish barriers that's been installed to keep exotic fish from returning to this landscape. And both of these things can have important conservation implications. So my objective is to evaluate the viability of this metapopulation based on these 2 things, fire synchrony and habitat connectivity. And my hypothesis is that the synchrony of wildfire increases the extinction risk, and the connectivity will decrease the extinction risk. The way that I chose to model this is using matrix population modeling. So This allows me to model multiple states, which are essentially a subgroup of fish that can be based on their location as well as their ages. And I can incorporate demographic variability. And then what's really neat is to disturb this model with future fire. So this is what the guts of it look like. This is Shingle Creek, one of the two tributaries. And in there you have some group of adult fish that survive at a 65% rate from one year to the next. Those fish give rise to about 1.36 individuals on average that are age 1 the following year. 45% of those fish become age 2, and 57 of those fish then become adults. So these estimates come from a really large marked population of Bonneville Cutthroat Trout in the Logan River. They're pretty reliable. And then this estimate I calibrated the model with to reflect what we actually observed, that fish were extirpated from about 50% of the watersheds where we saw them as a result of the fire. The numbers, I drew the numbers for survival from a binomial likelihood with this probability, and then a Poisson distribution with that probability. And then there are two creeks, right, Shingle and Fish Creek, where these same things are happening. And what I wanted to model is connectivity between these locations, as well as the incidence of fire. This is what the model looks like graphically. So on the x-axis, you see the number of years. I projected this forward 40 years. On the y-axis, the total abundance of this population. So there are about 500 fish in each creek, and then I ran this 10 times. I ran it a bunch more times than that, but just for the sake of clarity. So you can see 10 different lines here reflecting how this population proceeds through time based on those random draws of vital rates. And then down here is an extinction boundary at 10% of their former abundance. I'm also interested in looking at how this works when the populations are disconnected. So when the fish can't move from one location to another. This likely underestimates connectivity. This isn't the final version of this model, but it's currently ignoring improved growth or survival impacts that likely come from connectivity. Now I need to introduce fire onto this fish population and see how they do. And this is how I adjusted the vital rates for fire. So you can see, similar to the graph I showed earlier, that in the first year after the fire, the survival rate has been reduced about 90%, after which it recovers until in several years after the fire, it's actually higher than it was in pre-fire conditions. And then the two fire synchrony situations, this is an asynchronous fire regime, so you can see that there's a no fire condition, and then fire burns in one location, then it returns to a no fire condition and burns in the other location. Then in synchrony, it starts in a no fire condition, then the model burns both streams at the same time and then returns to a no fire condition. And again, I adjusted this to reflect what we saw in reality. And this was what I observed. So when the populations were disconnected, meaning fish couldn't move from one location to another, and fire occurred asynchronously, so it only burned one watershed at a time, you can see all 10 lines here. There's a drop when the fire burns in one location and a second drop when it burns in the second location, but none of these populations pass this extinction threshold, which is a 90% abundance reduction. When it's synchronous, however, you can see that 6 of the populations actually pass this threshold right after the fire, and then because of demographic stochasticity, a 7th one peters out about 20 years later. When those watersheds are connected, we see a similar trend, including about 5 of the populations were extirpated. So this was surprising to me because connectivity didn't improve it that much. What does this mean? So what we observed is that connectivity does improve the abundance. So the mean abundance at the end of the period was higher, as well as the certainty around that. And that asynchronous wildfire in neither situation caused population extirpation. When the fire is synchronous, connectivity is not enough. If you're burning the whole watershed at the same time, then these populations get so small that they're subject to a lot of demographic stochasticity, the Ali effect, from which they may not be able to recover. What this means is that this model I'm really excited about because it allows us to look at the mechanism of extirpation, to actually outline what it was that drove these populations to do what they did and identify those factors. And we can see that connectivity is important, but it's likely underestimated for my model, and that the fire regime is more important. Synchronicity is a big deal when you're dealing with metapopulations where fish need to be able to move from one location to another. But we know that these fish have evolved with fire, and they have adaptations to persist if we can provide them with a landscape to do so. So yes, we know that synchronous wildfire does increase extinction risk and connectivity decreases it. I'm going to scale this up in the future to include more than just 2 spots in the watershed, because there are a lot of streams. So again, a lot of people have helped me out with this, and I'm excited about it and where it's going to go in the future. And with that, I'll take any questions if we've got time.